Hi, and welcome to How to Restart.
Cut.
Hi, and welcome to Harajuku Data Lake. My name is Morris, and this week we're going to be talking about SHA-1 hashes and the shattered hash collision that Google discovered last week. So, just to jump right in there, Sergio, we have broken SHA-1 in practice, and we got a domain name about it. And okay, so I'm going to do a quick stab at what this actually is. So the end result is that we have a domain name, SHA1TERED, and we have two PDF files, PDF file 1 and PDF file 2. And if I download both PDF files and I do like SHA-SUM on both PDF files to figure out what the SHA-1 hash is of them, I get the same number. And this is very problematic because these two PDF files are different. They have different contents. And generally, if you do a cryptographic hash of two different things, you should get a different hash. So not getting a different hash is clearly very problematic. So today we're going to try and figure out a little bit more about what that means and what the actual impact of that is. So Sergio, do you want to start with explaining what a hash is?
Hi, good morning. Yeah, let's start on it. A hash function, okay, is a function that with the input, any kind of input, it returns always the same result, okay? Let's make the most simple hash function. The hash function could be, for example, that we insert any number we want, any binary data, and we always return 1. So this is a hash function. Every time that you have an input, we always return 1.
That's not a very good hash, Sergio.
No, well, it's not a very good hash, but it's a hash function. So it's very simple. It's something that it's very easy to understand. Then we have what is the properties, okay? But before going to the properties, I would like to mention something very important, okay? This thing that we are talking today is very, very related with the computers. And because we are talking about computers, this is our environment. We are talking that we have a network, a bandwidth, we have a memory, we have CPU, and all of these things, they limit or kind of range for do this algorithm, this function, okay?
Right. So I have I have a billion bytes of memory, and I have a CPU that runs, multiple million cycles per second, and each cycle can do a certain number of instructions.
Exactly.
And these are the limits of what I am able to do.
Exactly. So because we don't have infinite memory, because we don't have infinite CPU, we have to create a function that will vary kind of performance, okay? As I was saying before, these hashes, they have different properties, but these properties, they are also related to the limitations, okay? One of the most cases that we use a hash, if you are a developer, you will understand very easily, is the hash table. The hash table is, yes, you can imagine a table that the time that you spend getting the value for a key is O1. That it means that every time you request that, it's going to be a direct hit to the memory. Okay?
So it's not going to be exponential.
Exactly. It's not going to be exponential or even n or logarithm of n. So it's the fastest thing we can do. But the truth is that the implementation behind this hash table is not an infinite hash. It's just a kind of memory that we assign, and in this memory, we got something that is called collisions. These collisions, what happens when you are writing code, when you are developing a new application, and you are using a hash table, what happens internally is we enqueue these values in the same collision. So what it means, let's make an example. Let's go back and let's talk about this function n that returns 1. Imagine that if it doesn't return 1, it returns the same number but with the modular 10. So it means that when I insert 1, I will get 1. But when I insert 11, I will get 1. Okay, I won't get 11.
Okay, so this would be a simple like CRC function.
The CRC is a function that is for kind of integrity and to be unique, but the CRC is more is about the length, okay, of the hash. Depending of the length, is going to be stronger or weaker. Okay, so it's just another type of algorithm, but has some. This one, the CRC, has some properties that other hashes, like for example the MD5, SHA1, SHA2, they are different. Okay, so this CRC2 is very easy. For example, it's very fast. So when you want to have integrity, that works very well. Okay, but it's different properties. Okay, properties of the hash. So going back to the function I was saying. In this one that we have 10 elements, what is going to happen if we want to maintain the value is we are going to create internally, I'm talking about the implementation, we are going to create a queue. So what is going to happen is we are not going to lose any data. So when you are writing your code, you can use a hash table, you can use infinite values, but internally you are managing the collisions. Okay, but what happens when we have an algorithm that we cannot implement this kind of queue or mechanism that can handle the collisions? Okay, then we have a problem. When you have a same program that you can detect collisions, for example, I give you an example. You have a file manager. You use the hash for calculate from all the binary data of the file. Okay, we get all the file itself. We calculate the hash, and we know that this hash, the purpose for hash is to be unique with that data. We don't want another file with similar, okay?
Right.
So imagine that we have, for example, the file system. We can do a file system that if we check every time that we insert a new hash, so in the moment that we insert a new file, that this file has the same hash algorithm, we can detect that collision and we say, okay, let's handle it, okay? So the problem here is a problem of implementation and how we handle the collisions. Because right now we create a lot of programs that they don't care about the collisions because the hash is free of collisions.
Oh, so a lot of software is written with the assumption that there will never be a hash collision.
That's it. That's the key. That's the key of everything we are talking now.
Okay, so actually I want to quickly talk about what you mean when you say a hash table. So, a lot of programming languages have a hash type data structure where you have a key mapped to a value. When you say a hash data table, what are you talking about specifically?
Well, every language, they implement their own hash table, so it's different implementation of a Java hash table, of a PHP hash table. For example, talking about security, we have seen some mechanisms that they trick the function that was the collision function. So they made overflows to the memory because they hit this function. So the function that is handling the collisions is different. It depends implementation. We should go to the code and find the right code and read there and understand what they are doing because every language is completely different. Okay, so it's different. But what we know is that there are some limitations. Okay, about the space, the CPU, all of this. Okay, so going back to the start, this kind of hash algorithm, it let us to have an input, a hash, that is the function itself, and then an output. And depend the properties that we want, so it depends what we are doing, the business, the requirements, we are going to choose a different hash. Okay, but then going to the security side, and the SHA1, that is the one that has been kind of weakened, this algorithm, okay, was an algorithm that, as you said before, they didn't want to find another collision. They want to be free of collisions. That means that you, in a feasible time, you don't find another input that creates the same output.
So in a sense, it's, good properties of cryptographic hashes are these are algorithms that are actually incredibly inefficient on computing hardware, because we want to not be able to find a collision.
Be careful with the sentence. Be
Okay.
careful, because especially these hash functions, and they are related a lot with the kind of cipher functions that we can talk a little bit later. These functions, when you implement them, you are preparing the hardware to be highly efficient with the hash. So what it means is, internally, this hash function is using another functions that they are, for example, a shift function, a summatory, that they are very efficient in a CPU.
Right.
Okay? Because every time that you calculate the hash, you create like iterations, okay? And every iteration you are changing this result, this output. For example, SHA1 has 80 iterations, okay? And they are separate by blocks.
80 iterations.
Yes. So they are separated in 4 blocks, okay? 20, 20, 20, and 20, and they are different kind of algorithms, okay? And this must be very efficient in a computer. There are other hash functions that they have been designed with other purposes, that they are going to be, for example, slower. For example, the bcrypt function. The bcrypt is a function that is being used for create a hash of a password. That what it does, it executes the same function several times itself. So it means that if one function, it takes, for example, 100 milliseconds, if I execute the same functions 10 times, I'm going to take 1 second.
So taking the output of one function and then putting it back as the input again to the same function.
That's right. That's the idea. So with this idea, what we create is a hash algorithm that for calculate back, so it means if we want to brute force the algorithm to find the original input, we have to spend so much time. So because we don't have enough CPU time, okay, enough CPU, we cannot reverse this hash algorithm. Okay. At the end, remember something very important. When we are creating a hash, we want to have a huge or infinite data into a kind of not variable but static length result.
Fixed length.
So yes, fixed length. So we are losing information when we process a hash function. We are losing information. So that's why it's possible to create another input that match the same output that the first one.
Yeah, so like in the case of SHA1 is a 160-bit long hash. So no matter how much data you put in, what you get out is 160 bits. So what that means is that there must be, since we're putting in more than we get out, there must be 2 things that if we put in, we get the same value out. And effectively what we have with these 2 PDFs from Google is 2 things that we put in that we get the same 160-bit chunk of data out.
That's it.
Okay, so I think one thing we briefly touched on was properties of cryptographic hashes. So when we talked about briefly about bcrypt, you were talking about not being able to reverse the hash. And that's definitely one of the important properties of cryptographic hash functions, is that from the output of the functions, you're not able to recreate the input.
Yeah, mainly that's for this kind of family algorithms. Yeah, that's the purpose.
Okay. Do you want to talk about other important properties?
I think that, as I said, we said the shared C, for example, is a function that it lets you to have the kind of fingerprint. So it's very fast. So you have a huge file, so it can be several gigabytes, and this function is going to take some information from this function, and we can be almost sure that file has been, for example, has been compressed only once. Okay, so what I mean is that, as we said, there are different properties, and not all of them must be true. For example, when we are creating a hash, we don't really need to be always true that it must be perfectly accurate. For example, there is another function that is called and B, that this function is very fast.
FND?
FNB.
Okay, FNB.
This one is very fast. If you want to create unique IDs from a large data, you can use this function to say, okay, how many. This is used also in the Bloom filter. The Bloom filter is for, okay, I have million of users, but I want only to use this number of memory. Okay, a short memory, because I have million of users, million of events, and I want to count the number of events every time, and I want to use few memory. So this hash, and well, this kind of full algorithm, because it's a full function, this function must be quite accurate, and with the estimation of an error, he must be telling me, okay, how many hits we had of every event. But I'm not counting every event. I'm just counting like an average. Like, okay, I know with an error of 1% that I have 3,000 users, okay? Or I have 3 million of 3 billion users. So with the estimation, we are getting a number enough good, okay? And this is done also with the hash function. It doesn't have to be safe. It just must be accurate. Okay? So I think that it's important to understand that the hash function has different purposes, and every purpose has consequence. So it matters a lot in implementation. One of the first things that they tell you when you are studying really cryptography in deep is that don't ever write your own class for implementing a hash or a kind of cipher function. Why? Because it's very difficult. You don't have to care only about to write the algorithm. That is something that you can read the pseudocode and it's easy. But the problem is, imagine that you use a machine that is multi-thread. What is going to happen? For example, there are several attacks. Maybe it's another topic, okay, related. But there are several attacks that you can measure the bits that they are in the circuit itself of the CPU, so you know what is happening. Okay, this is a side channel attack. Okay, so this is a bit more complex, but you have to be very careful when you really implement the algorithm. Even in implementation, that's terrible. But in this case, and going back to the main topic, that it's the shattered SHA-1, the problem that we found here is a collision attack. So right now we know that it's possible. Is potentially possible to have with creating one, for example, in this case is PDF, but in PDF we can get another one that has the same signature, the same hash. Okay.
Okay. What I'm trying to get you to say are like the
Sure.
So on Wikipedia there's this article called cryptographic hash function. And it says the ideal cryptographic hash function has 5 main properties. So it's deterministic, it's quick to compute the hash value, it's infeasible to generate a message from its hash, a small change in the message produces a big change in the hash, and it's infeasible to find 2 different messages with the same hash value.
Yeah, well, as I said, at the end, it depends what you want, that you have to choose different properties. You don't really need all of them sometimes, because as I said, you need to spend, well, you only have available a short range of memory. So it depends what you have. You have to choose really your kind of hash. Right now, for example, we are not using a kind of longer hash, because every time that you have the hash and you want, for example, to verify a file, you have to send all the hash with the file. So this is a lot of network, a lot of bandwidth. So we are using this kind of short one, like SHA-1. We are using SHA-1 instead of SHA-2, because the 2 or the 5 is longer than the SHA-1. So when you are sending a lot of information, imagine that every packet that you send through the network, you are checking the integrity. So every time you are sending these bits, so there is a moment that is a huge amount of bits through the network. So that's why you are choosing the smallest one, but it ensures that it's not broken.
Right. Well, and often in like transmission protocols where like authentication, where is not as important, you will use something like a CRC, which is both very small and very fast, as opposed to a cryptographic hash function, which takes more time to compute and might be longer.
Yeah, but you are saying something that is very important. You are saying, okay, once that we are got authenticated and we are authorized, in that moment we start using something that is not so safe, not so secure. That's right, because the first one was using this kind of functions. So right now we are with this SHA-1, we are breaking the first algorithm. We are breaking the kind of digest handshaking.
Right.
So the problem is not later. The problem is when you got authenticated.
Okay.
Okay.
All right. Did you want to talk about differences with the cipher algorithm briefly, or head on to what is this specific shattered attack?
Yeah, I think it's better if we go directly to the SHA-1 because it's just a kind of, as I said before, properties and, okay, what is the more mathematical things? Everything that we are talking about ciphering, cryptography, this comes from mathematics. So in the moment that you are, for example, I did the course of cryptography, and in that moment they start with advanced mathematics, and you are using a matrix, you're using a generator, you're using some functions that I think that right now is not the moment to talk, and even I don't remember all of the concepts. So,
well, and this is actually why engineers don't really particularly like to talk about cryptography and often have trouble implementing cryptography, is because it is actually deeply mathematical, and we might not actually be very good at math.
I personally don't agree. I don't think that this is the true. I mean, I think we love to talk about this. I mean, we can go specific and start talking about something very, very specific. The problem is that if we talk about this, it's going to be useless. Because as I said before, when you are doing something really professional, you have to believe the implementation for other people. And these people, they are really cryptographers who invest a lot of time preparing the function, ensuring that everything was right. So you want to delegate, okay? And we can talk about, okay, we have this function, and maybe it's like it's worth to spend time telling you how it works in something very concrete. I mean, it's very difficult to talk about this topic just in large, in like, there exists hash function. Okay, but what do you want to do? Do you want to do something efficient? Do you want to do something that is iterating 200 times? What is the goal? No? So in the moment that we talk, I can say, okay, but before all this kind of chit chat, let's say what is true and what is more important. And what is important is don't write your own functions, because there are so many attacks that you don't even know.
Right.
You have to be a kind of specialist for knowing these things. So I have right implementation of these, and I have do fuzzers, and I know, but because I know, I am not gonna do that. Okay, so it's a kind of you can, for example, you can see a doctor how to do an operation to a patient, but you don't want to do that because there are so many things that he's deciding in the moment he's doing the operation that you don't even know that is this happening. So because I have more more knowledge about this topic, I can tell you, well, let's avoid this.
Right. Well, it's the paradox of, like, if you are truly ignorant about a subject, you don't know what you don't know. And because you don't know what you don't know, you're even more dangerous than somebody who knows more.
Yeah. Yeah. But in the moment that you get some kind of algorithm and you start talking about, oh, but this function in this kind of CPU processor, it will be easier to process. So this takes 1 millisecond, and this one is 2 milliseconds. And if you use a GPU, it's gonna be faster than. So you can do, for example, all the kind of bitcoins. It's based on this mathematics. Okay. So you start talking about this deeply with someone who understand the base, and even you explain to him like what you want to talk about, and I think that's the real purpose. But to be so global to someone who doesn't understand about the topic, I think is too much, because when I say a sentence about ciphering, I have so many implications. I'm sure that everything I said, it can be like, but Sergio, wait a second, maybe this is not true in this kind of situation. Well, maybe. So that's why I'm a bit careful about, and I don't want to go kind of deeper, because then we have to go with the kind of hypothesis, like, okay, if we have this input, then a function done this, and you define so many things, and you need the context. Okay, so that's why it's difficult to persons just start talking about, oh, is a hash good or bad? It's like, well, there is not a response. No, it's useful if you need, and you know when you have to use, and in the moment that you have, for example, a program, product that it is using these kind of functions or cipher functions, then try to use something standard and that has been proved, no? Because there are organizations that they have spent a lot of time and money just to make that good enough. And in the moment that, for example, right now Google spends so much money to show to everybody that there is a collision, is because they want to make you awareness that there is a huge problem over there. So everybody that is using right now SHA-1, please start moving to another SHA-2, SHA-5, depends, okay? But they are telling you like, hey, be careful. We have already find this kind of problem, so maybe a kind of terrorist organization maybe could use potentially for that. So they are trying to advise you, like, okay, nothing is gonna happen. We haven't crashed the war. Don't worry, because as I said, maybe you are having the hash, but what happens in GitHub, okay? In GitHub, what they have is in Git.
Well, before we get to Git, like let's go to the next. Like, what is the shattered attack?
Okay. The shattered attack at the end is to find another collision of one PDF file. In this case, they made a PDF file. If we go deeper to the internals, okay, what happened is they use combinations of all the old material, so everything that they had already found, they use that thing. They also use another thing that is very important, and is that they pre-calculate only for a kind of a structure. So they use a PDF structure. So it means that they knew forehand, they knew what was the bytes that was in that position. So they already knew that, okay, this is a PDF and we are going to create another PDF. If you give them, for example, another file or just binary data, this is going to be possible, okay? You need to pre-stabilize some kind of data. And they choose a PDF because, well, it's huge. And they use a JPG inside a PDF, okay? So they are kind of cheating, but that's true. They are like kind of cheating, but they are making you like, hey, this is potentially problematic, okay?
Right.
So it's not like that's completely done, but it's like, oh, there's one collision.
Yeah, so they're taking advantage of the fact that to a layperson, the PDFs appear visually to be exactly identical, but PDF files have space in them to contain arbitrary data. They are putting things in that arbitrary data that makes oh, wait. Oh, never mind. Sorry, I'm mixing this up. Okay. Okay, so they have two PDF files that appear to be different. And they are
different.
And they are different. Okay, these are two PDF files that are different, and within PDF files there is space for random bits of data that isn't displayed to the user, and they're putting random junk data in those spaces to affect the resulting hash of both PDF files. Okay.
Yep. Yeah. At the end, what they have is one that is a legitimate PDF that probably it contains, for example, a snapshot. You for example, you create, and this there are several companies that they do this. That, for example, they want to be legally sure that a web page had a status, a state. In a moment, okay? So they take a screenshot and they upload the screenshot inside a PDF, and they create a SHA-1 of the PDF. So they are sure that the PDF that contains the screenshot is always the same, So this is a signature, and this can be legally used. And in the moment that you are able to create a file that is trust data, young data, in that moment, you can say, okay, but this could be done with this other PDF that is nothing. So in that moment, legally speaking, we are breaking all the trust on this PDF screenshot. Okay, so that's why they create a PDF inside the image.
Okay. And the way they actually did it was, so this, so a pure brute force attack where you're you can have infinite inputs to these functions. So a pure brute force attack is not actually feasible, but what you want to try and do is, instead of, trying 2 to the 160 different combinations, you want to cut that down so that, with this thing you're only trying 2 to the 80 combinations, or with this extra hack you're only trying 2 to the 69 combinations, or with this extra hack. And as you reduce the number of computations you have to do, at some point it becomes feasible for a system with, they said they used they were able to calculate this hash in effectively 110 GPUs running for 1 year.
Yeah.
Which is totally, it's something that with a little bit of money anyone could do well.
Yeah, for example, with all the CPUs and GPUs that they are using for the Bitcoin chains, the chains of Bitcoins, they could break it with several days. Okay, so it's possible, but of course nobody is gonna use right now. But it is at the end, what happened here is it was a research center that they have very good cryptography people, and they designed the kind of algorithm that was for make this kind of weakness, and then to be able to calculate with this number. And these guys, they asked Google for some help, and Google said, okay, I put the machines for making this possible, no? And well, both of them, they join and they create this tool that we can check a PDF. So, but you need so many GPUs and everything. So, and you must, as I said, you must know the kind of structure that this is gonna start, no? So if you have some raw data, this is gonna be possible right now. But if these guys got this, they arrived to this stage, this is telling you that maybe in 4 years we have something that has a collision in any kind of binary data, because they find something that is, or well, we have faster computers, so we know that we are getting advantage every year.
By the way, what does they have a file tester on this website that says, drag some files here and we'll tell you if they are part of a collision attack. Do you have a sense of what they're doing there?
Yeah. Well, and there is in GitHub, there is a program that tells you a little bit what is happening, and is the same that they said about what is checking is vectors. It's vectors like, okay, I know that in this position from this byte to this byte we have these numbers, and only these numbers. If you change one of them, that's over, because they know that. You remember when I define a little bit the hash function, and I said the SHA1, it has 80 iterations, and the first 20 has some algorithm, the next 20 has another one. Okay, so the first ones, they have been analyzed. They are okay, if we know that the data that you input is this, in the next state is gonna be like this. So they have already all this kind of they can bypass these iterations. So they are what this tool is doing is it checks that in these spaces there is this information. So in the moment that you are using a PDF and this PDF hasn't changed something dramatically, they detect that, okay, we know that everything that we pre-calculate is gonna match after the iteration 23. Okay, so they have a part of the iteration 23 that is already pre-calculated. I recommend, if anybody is interested, I recommend the page 19 of the document that they have, the PDF, there is a very interesting graph. It's the figure 3, the differential path of the second block up to A23. And with some symbols, they are making you to see how from the initial hash that you have, okay, the original one, this goes like changing small, little by little, and at the end in the 23, you only have 3 symbols. So you can guess that data is like that in that step. But the dots, they are like, okay, we don't know. We don't know. So these guys, they pre-calculate all of this stuff that they have in this figure. They know all the symbols, and they don't know the dots. So the dots is what they pre-calculate. So if you start with the message that matches, you are going to know after this step. So this is a reduction. This is like they weak the algorithm, and they are using brute force to calculate all the iterations, well, everything that they can possible, all the possibilities, and that's it.
This is in the paper that they published.
Yeah.
What page is it on?
19. Okay, so they are doing some kind of simulation, or like, okay, with his, but this is just pure mathematics about, okay, this is you see down the symbol and the table, the condition. So, but I think that's too much. I think that they just use a lot of information. They reuse everything that they had already discovered, other researchers. So they just improve it with some kind of predictions, and making this kind of static from the start. So that I think that's the important point, and this is where they did it very well. And well, they got a program, a tool that make you check if it has got a collision. So that's enough. That's enough for make aware all the community. So end user should not be so worried about. But all the kind of developers that they are maintaining something and they are using SHA-1, this is a huge recommendation to change to the next one, to SHA-256. And yeah, be careful about if you are saving, for example, you are storing your SHAs into a database that has maximum length of the SHA-1. So maybe you need to change the size of your database, and if you are using a legacy system, maybe this is a problem, because you have to migrate several kind of gigabytes, petabytes, whatever, bytes.
Yeah.
So
well, it also depends like why you're using a SHA-1. I mean, it may be that you're not actually trying to use it for any of the you just want a basic hash, and SHA-1 happened to be a simple hash, so you just use SHA-1, but you're not actually relying on any of the properties of a cryptographic hash.
Then you are a bit stupid, because then you could use another thing that is more fast to calculate. Because a SHA-1 it takes time to be calculated. So maybe you choose the wrong thing. So maybe if you no. If you were using SHA-1, it has a reason, no? So maybe right now that we have that is like broken, what is like, okay, there is a huge recommendation to move to the next one. So at the end, of course, maybe you are not affected because as the people of Git, no, that they have also the length of the file, so it's more difficult to find another file with the same length, with the same hash, no, the same fingerprint. So I mean, I think you have to just review what you do. But I think that if you are using SHA-1 and you have a proposed, you should really care. We have to say, and before, when you gave that example about the communication, we said that, no, that I am not so concerned about in the moment that you are already pre-authenticated. I am concerned about this authenticated system. No, if you look at the infography that they upload, and you see the potentially impacted these systems, everything that we are talking about is very kind of sensitive data, no? Document signatures, HTTPS certificate, version control. for example, let's remember that one of the kind of virtual control system, I think what's Mercury, if I am not wrong, it was like it crashed because they upload two PDFs to the systems. Okay, so
that's SVN, isn't it?
SVN,
like,
SVN.
Yeah, so like people are just trying to upload these two like if you upload two things, because SVN is using SHA-1s for deduplication. If you upload two things with the same that have the same SHA-1 hash, all sorts of crazy things happen.
Exactly. So maybe in that moment, if you had another implementation, just giving you a warning and saying, hey, error, there is a file that exists with this. So maybe in that moment it was, or it just overwrites the old file. But what I mean is that depends what you want, then you have to decide. In this case, it crashes system. Okay, congratulations. Okay, and the next one is backup systems. Okay, so the four of them, they have sensitive data. So that's why it's so important. If this will affect only something random, it doesn't matter. It happens like every day. Every day we are having a lot of technical debt, a lot of products that they are not exactly as they are. All the kind of security bugs, they are there. But this one affects to like everything. Why? Because we trust in that function. This function has been validated by an organism that spend, as I said, a lot of money, a lot of time. They make a kind of quiz for choose the algorithm. So they had so many candidates. They present some mathematics. They search like, okay, is going to be any problem? Is it safe? Is how much is going to take in my CPU in this design? What is the kind of libraries depend of your architecture of the CPU? It matters a lot. Everything matters, and we are talking about a lot of cycles of CPU. So this is everything has been very carefully picked. You know, it's like they decide it very carefully. So we have to be very like prudent, no, when we are deciding, oh, we want this one or that one. But yeah, that's it.
So actually, I mean, it's been known for a really long time that SHA-1 has been vulnerable. It hasn't been recommended for a relatively long time. Like, I think in the US, the National Institute of Standards and Technology, NIST, has a recommendation against using SHA-1 that looks like dates from around 2013 for public key infrastructure for like TLS and certificate signatures. There's been an attempt to move browsers away from trusting signatures that are signed with SHA-1 for several years, and I think this SHA1TERED collision really made the point that was actually an important effort.
Yeah. The problem, as you said right now, is several years, no? For several years. But do you imagine in the 80s that they were like, oh, SHA-1 is the most safe and it's never ever going to be destroyed, no? So right now that we can recommend to use the SHA-4096, okay?
Really?
We can.
Okay.
No, we can choose another one that is gonna be stronger, just longer size. So right now we can be with, or for example, with deciphering. If we talk about the elliptic curves, we can say, oh, that's the future. That's amazing. This is they are right now. But 20 years ago, 30 years ago, that was like, okay, impossible. And we are talking about systems that they are banks. They are very old legacy systems. We are not talking about Facebook, if Facebook is using this one or not. Maybe they have their own implementation. For example, the other day, a news that is interesting to say is, to mention, is Amazon. They just changed completely what is OpenSSL for a version, a custom version that they have. That SSL, I think it is like 600,000 lines, and this implementation is just 6,000 lines. So they changed all the systems. They migrate all the systems to the custom and easier to read and easier to maintain implementation. So when we are talking about these functions, we have to go to the past and say, hey, who is still using, and can you really migrate the system? Can you, for example, if you have bank information and you have transactions and you create a SHA-1 for every transaction about this amount, maybe you can now create another identical transaction from another user to other, no, from one user to
Mm.
another user, and you can manipulate something, no? So when we are talking about security, always, and right now it happens, you don't use one bug. You don't use one vulnerability. You combine several of them. So it's in that moment that is problematic, no? So right now, what happened,
Right.
okay, what happened with the Shattered is the kind of awareness is that they discover something that is potentially be hitting in the next years. So if you are a developer, please start changing. There is another example. Let me word that example.
Mm-hmm.
Is the when it was the 2000 year, you remember?
Oh yeah, year 2000.
Yeah, so many clocks, they were not designed for have more than 16 bytes. So these clocks, they had only one date. Okay, so they didn't were able to manage to be the 2000, and there were a lot of embedded devices, kind of alarms, kind of elevators, kind of all this stuff that was not updated to handle this error. Right now we are using a Unix timestamp, and because we are using 32 bytes, because we want bits, sorry, no bytes, 4 bytes.
32 bits.
Yeah, 4 bytes. No, 8 bytes. 8 bytes.
This
Well,
is why we can't talk about math, because we can't even do arithmetic.
Okay.
Sorry.
So the problem is that the 2038 we are gonna have another problem. So in 21 years we are gonna finish the number of the Unix stamp. So in that moment we are gonna have another problem. And the question is why we are not migrating to that? Well, because we have still, and it's changing a lot. It has changed in the last years, has changed a lot. But like all our systems is 32 bits. Okay, so because we are using a 32 bits architecture, we are still with this number as the count, okay, to know which year is this. But we can migrate to a 64. But a lot of devices, micro devices, embedded devices, they are still not like it's cheaper, no? It's quite cheaper to maintain one lower number than a huge number for the date.
Okay, so just to reiterate that, what you're saying
sure.
there is that so Unix timestamps are it's like the number of seconds since January 1st, 1970, and it's represented as a 32-bit number, which is 4 bytes, and the number of seconds from January 1st, 1970 is, well, let's see, you only have 2 to the 32 possible seconds, and that number of seconds, if you add that to 1970, you get 2038. So sometime in the year 2038, we will run out of time that we will be able to represent using a 32-bit timestamp.
Mm-hmm. That's it. But that's another example that is the same that happened before, and it's happening right now with the SHA-1. So
yeah. The other interesting thing is that these things, I mean, so MD5 was another hash that was really, really popular in the 90s. And even today, occasionally you see MD5 signatures here and there.
Yeah.
I mean, it's not usually hopefully you don't see them in security sensitive applications, but once people are used to using particular tools, they just, they use MD5 because they've always used it, or because they wrote the system a long time ago and nobody's updating it. And these things tend to stick around much, much longer than you would expect.
Mm-hmm. I think, and that's my personal opinion, but I think that MD5 is so popular because they got a very good kind of a huge marketing. Okay, so everybody with PHP in the moment of PHP, and everybody was over there starting, they could use the MD5 function very easily. They only needed to do MD5 parentheses and some value, and it worked. And for them, it was very wow, it works, and we can do everything we want. We love it. That's it. I think that is a problem of divulgation. About that, everybody just knew that, and That's it. In the moment that you start reading a little bit more and you understand what's the consequence and what is the length, and but I don't think that the people that they are using that they really understand the consequence. I think that it's popular. It's popular. That's the reason. That there is nothing else right now. We hope, no, that with this kind of fancy names, like Shattered, the Cloud Bleed, and these names, everybody's more kind of, there is more publicity, more announcements. Everybody's more aware that this is happening. So it's just to reach everybody and say, hey, don't use this, don't use that, because the people, they are not specialists of these kind of things. You need, as I said, a lot of mathematics for really understand, no, the concepts, and I think that MD5 was just popular and easy to use. For example, have you seen or have you implemented any time the HMAC function?
No, I haven't.
No. It's normal. It's something very useful, but it's like, well, I need several parameters. Or for example, when you are doing ciphering and you need the prevector, okay, it's called the AB. This number is something that is like, oh man, but which one is this number? Can I use a random one? Can I leave it like nil, like no space? So this makes weak the algorithm, but they don't know because they want something simple to use. So even you don't understand all the kind of mathematics that, as I said, is something that you learn once and later okay, you understand forever, but you're gonna forget. Okay, that's completely overhead. You are gonna understand that this is you must be very careful because there is so many implications that you don't really know. So, yeah.
All right. Any final thoughts about SHA1 and Shattered that you want to share?
No, I think it's very cool. No, what they did is kind of researching center with Google, and Google, that was so nice to say, okay, I'm gonna start so many machines free for you, and we are gonna do this. No, that this is gonna be history. No, there will be a moment that, okay, this day we just said that this one doesn't work anymore. No, it's a collision. No, that's the kind of it's popularity, as we said. Like we are famous, no, people in the cryptography world. But I think it's very very cool that they prepare something like that. And yeah, we have, I think, the governments, we need institutions that they research about this and give, no, these tools that they are more safe. And we have also to be very careful, no, with the implementations, right, that we prepare. And for example, if you are creating a new framework and you are creating your own implementation, you really try to find some assessment from someone who really knows and ask some friends. And I think that this is a very very sensitive topic, and it's very easy to say, oh, that's broken, but why is this broken? Why? How they? What we have been talking about? Okay, these guys, they have been cheating with the kind of predefined structure, but well, cheating works. So they haven't really cheated. It's just they did with a pattern. Okay, do the same. Please do the same. If you can, do the same. So yeah, these guys, they are really worth. I know one guy, for example, in Spain. He went to one of the biggest conference of security, and he said that he had broken the algorithm for the SSL 1.2 or 1.3. I don't remember. And he was like, oh, but I am not going to show you how I did. I'm going to tell you how I did that, no? And everybody was like, are you sure that you broke it? Are you sure? yeah, I did. And later, of course, they discovered that this guy, he never broke it. He was using something that was already, I don't remember exactly, but it was like, okay, it's normal, no? If you know the key and you have already pre-calculate, if you did that, it's like, it's the same like we're talking about WhatsApp, no? That, oh, if you are able to do a man in the middle when you are interchanging the keys, then you broke the algorithm. Of course, in that moment, that's the kind of design that we're using. So in the first time in the WhatsApp, you are having you pre-establish the key. If this key is stolen because you don't trust to the other agent, the other party, then that's completely normal. So in this case, it's the same.
Yeah. So actually, one final thing.
Sure.
So as developers, Git is probably the most popular version control system at the moment. Git uses SHA-1 hashes heavily. Is this something that you're particularly worried about?
No, not at all, not at all. I think that the guys that they are behind Git, they know very well what it is. They know that right now they just found this kind of, okay, we can do these collisions. That's something they are aware. Linus Torvalds itself, he spoke about this. The security, the design is not compromised, but I am sure that they are gonna release new versions, that they are move to new kind of collision management algorithm that maybe is the SHA-256, or maybe they know because they analyze and they prove that it's more difficult to find it because they have the length of the file. I don't know how they are gonna handle, but in the next version, I'm sure that in the moment that you update the repo and you just update your version of the Git, this is gonna be enough. So I'm not worried. They can manage the collisions. That's fine. If they manage a collision and they just have to print you an error saying, "Hey, this is a collision of another file." That's it. That's more than enough. So that's the implementation. So I'm not worried at all. No, not at all.
Okay, so because they're also saving the length of the file, it makes it harder to create collisions, and they are, to some extent, they are using SHA-1 hashes for security purposes, but for average developers, they might not actually be relying on the security functionality present there. And do you think that they have a little bit more time before they have to switch to something else, and you're pretty confident that by the time that they will switch to something else pretty soon?
Yeah. I am more worried about the kind of, for example, routers. A router that has been shipped and you buy the router, and this router cannot be updated because there is no any mechanism, or if you update, you are gonna break all the compatibilities with everything else at the device. That's what I'm worried about. Every time that we have this kind of SSL problem, for example, what we have to worry about is the kind of devices that you have it hard code. In the moment that the Git guys they can change all the logic, they can make a conditional. That's fixed. They know the problem, so that's fixed. I'm not worried at all.
Right. It's like the consumer devices that rely on having that can only support certificates signed with SHA-1 hashes, and they're just going to be sitting around in people's houses for the next 10 years, and will never get updates, etc., etc.
That's it. This is a kind of problematic, because we are talking about, and maybe we can do a chapter about this, but we are talking about devices that once you buy them, that's like, okay, they are never gonna be updated, and in some years that's terrible. What they have over there is terrible, but that's a problem. I mean, sorry, let me reformulate the answer, and is the problem is these products that they are in the technical market, so they are software development, they have something of software, but they don't really care about the software. They don't understand what it means to ship something with the software that you cannot update again. Okay, so it's the same like what happens with the cars. No, we have seen with Tesla that the guys of Tesla, they just need to upload a new firmware, that this one is validated, everything has the proper mechanism, and it updates the car. So in a second, all the cars of the world, they are updated with the last version. So if they see something new, that can fix very fast. Okay, but imagine other cars that they don't have this mechanism. That's terrible. Okay, that's that. We have to go take all of them, change the firmware in the company, in the factory. That's you cannot be in the technical software market if you don't really know how to handle these kind of errors. Okay.
Right. And like, 40, 50, 60 years into the computer revolution, there are still so many industries that even though they're producing things that have chips in them, don't fundamentally understand how computers work.
Yeah. That's it. I think we love to talk because we have been here 1 hour. So
Okay. So thank you everyone for listening, and we are on iTunes now, so please like and subscribe and tell your friends.
thank you very much.
Bye-bye.